Okay, so the last class, right, we started discussing non-dimensionalization. We said, given a number of variables, we don't want to deal with all of them. So what is the best way to reduce it, right? So we took some simple equation and then we started non-dimensionalizing it. And then we found that, it could indeed be reduced. So the expressions, the simple expression that we had was that of the trajectory of a falling particle, and if that was actually given as s equal to s0 plus ut plus half gt square, depending upon what method you adopted to non-dimensionalize it, you could write it typically as a non-dimensional distance as a function of a non-dimensional time and some additional parameter. That's all what we had done, right? Then I said, and in this particular case, okay, in this particular case, we knew the equation and therefore we could go ahead, but typically that would not be the case. Okay, so what is the general way of doing it? Before we discuss that, let's look at non-dimensionalization of the governing equations that we already know. Okay, so we are going to look first incompressible Newtonian fluid, and we will do the same thing that we did for the trajectory of the particle and see what non-dimensional parameters are going to come out. Okay, so that's going to tell you how, what is the most important parameter that determines the fluid flow. Okay, and then we will look at, when we do not know the equations, how to proceed. So we are looking at a very general system. Okay, we have some fluid which is flowing and we want to describe the dynamics. We will write down the governing equations, which would include the continuity equation and the momentum conservation equation. So let's just write it down. Continuity equation for an incompressible fluid would be simply divergence of u is equal to 0, and then we have momentum conservation equations, which is rho times dou u by dou t plus u dot grad u is equal to minus grad p plus mu del square u, right, in a general coordinate system. And you will additionally have boundary conditions, which would be, some velocities that you must, either u is specified, which must be 0 or something else depending upon the problem. So this is typically what the problem would look like, right? So now so the difference between the previous case that we considered and this is that in the previous case it was just an algebraic equation. This is a partial differential equation. That's the only difference, okay, but otherwise there is no difference, and therefore there is no difference in the way you want to non-dimensionalize it also. To non-dimensionalize, we need to select some scales. We yet don't know how many scales we should choose, but in this case I am going to tell you how many we will select. Okay, we are going to say that we will have a characteristic velocity, we will have a characteristic length, and we will have some characteristic pressure. Okay, so that's what we are going to do. We will select, let L be a characteristic length in the problem, let U be a characteristic velocity in the problem, right? So that means I can non-dimensionalize all my length with this capital L. Okay, so if I have a coordinate x, I'll define an x star is equal to x divided by L. So is my y star will be y divided by L, z star is z divided by L, any gradients, okay, spatial gradients which are grad, the non-dimensional form of grad star would be grad non-dimensionalized with length inverse, correct? Velocity, so we have a velocity again ux, uy, uz. I'll say my u star is u divided by some characteristic velocity. My t star will be t divided by L by u. Okay, any doubts? Pressure. Now, there are various ways to do this, okay, and we have seen this, and so we discussed in the last class that it really doesn't matter what exactly we choose, right? What exactly we select to non-dimensionalize. I'm going to suggest that we will non-dimensionalize pressure by a quantity rho u square. Okay, one way of thinking about it is that if you look at Bernoulli's equation is really P by rho plus half u square plus gz, right, is a constant. So you can see that P essentially would be like rho u square, or P could be like rho g z if actually hydrostatic pressure was more important. Okay, so by really selecting P is like rho u square, we are saying that okay, in the problem it's likely that my pressure will be, you know, acting like my rho u square. That's the only reason we have selected it. Okay, okay, so those are my non-dimensional variables, that list. So we can go ahead. So this is what you see on the right hand side is my non-dimensionalization. So now we can go ahead and substitute and see what happens. Okay, how many reduced variables we are going to get. So the first equation again is continuity equation, which is divergence of u is equal to 0. So if I use my non-dimensionalization, that tells me that L inverse grad star dotted with my velocity u times u star is equal to 0, or L inverse. So that means L inverse u into grad star dotted with u star is equal to 0, or simply L inverse and u are like numbers that we have chosen in the problem, which can't definitely be 0. So it simply says that del star dot u star is equal to 0. Okay, so the continuity equation written in the non-dimensional form did not bring in anything new. All the variables remained as such, except that they have become now non-dimensional. There was no non-dimensional parameter that came up during the non-dimensionalization. Now, if you remember, we had done something very similar when we derived the equation for flow between plates or tube flow, one of them, where we did the non-dimensionalization. Does anybody remember? We had a differential equation. We actually non-dimensionalized it with a characteristic length, a characteristic velocity, and we ended up with something very similar. There again, we did not have any non-dimensional parameter. Okay, so this is something very similar. In other words, the continuity equation basically, you know, whether it's dimensional form, non-dimensional form, whatever it is, there is no parameter that is going to be prescribing what, you know, the mass conservation is. The mass conservation will be just given by that, okay, irrespective of what the flow parameters are. That's all. There is no particular parameter that you can identify which could actually change the way the solutions are going to be, just because based on the mass conservation. So now the momentum conservation. So we have several parts. We'll take one by one. So we have an unsteady term, then we have a nonlinear term, then we have a pressure term, and then we have a viscous term. Let's non-dimensionalize each of them and substitute. First term is rho times dou u by dou t is equal to rho times del of u is my characteristic velocity times my non-dimensional velocity by del t, we wrote it as L by u times t star, which is going to give me rho u square by L times del u star by del t star. So, that is the non-dimensional form of the unsteady term. Then we have the non-linear term rho u dot grad u, which is the next term, is rho u is u star times u dotted with gradient is L inverse del star operating on u star u, which is going to give me rho, sorry, this is not there, rho u square by L into u star dot grad star u star. Correct? Where? Rho, so you're talking about the left hand side or the right hand side? Left hand side, it's just rho into u dot grad u, right? The second term? The second term is just rho times u dot grad u. Or if you are not comfortable doing this, we could do it in the Cartesian coordinates. Let's say we can take this. What is this term? Let's say for the x momentum equation, it will be rho times ux dou u by dou x plus uy dou u by, so this dou ux by dou y plus uz dou uz by dou z. Maybe you could do that and verify that it's the same answer. If you have doubts, if there is something that's not clear or you are not able to understand, please ask. So what we have is this term rho times u dot grad u, right? You have a rho and then u dot grad u. So you need to non-dimensionalize u, you need to non-dimensionalize grad, and again you need to non-dimensionalize u, right? So I'm going to substitute for the vector u, I'm going to substitute for the gradient operator. So how does one non-dimensionalize u? We defined the non-dimensional u star as the vector u divided by a capital U. In other words, this u is going to be just capital U times u star. Similarly, our grad is going to be just L inverse times grad star. So this will also, if you do it component wise, you are going to end up with the same equation. Okay. So remember, we have used the same characteristic velocity for all velocities. So for ux, uy and uz, we are using the same characteristic velocity. For x, y and z, we are using the same characteristic length. Okay, otherwise it's going to give you different combinations. So at the moment we are sticking to the simpler case where there we are not really distinguishing anything with respect to any directions. Pressure term. So let's look at pressure. Pressure is what? Minus grad P. So that's equal to minus grad star L inverse acting on pressure. Pressure we said we will non-dimensional it as P star rho u square. So you're going to get rho u square by L times minus grad star P star. And the last term that we have the viscous term, which was mu times del square u, which we can write it as mu times L to the power minus 2 del star square operating on u times capital U, which is mu u by L square times Laplacian of u star. Let's go back and substitute in the equation now. So let's look at the terms. The unsteady term was rho u square by L into this quantity. This is also rho u square by L into same thing, minus grad P, very similar, and this is the only term that's different. So we have rho u square by L into dou u star by dou T star plus u star dot grad u star is equal to rho u square by L into minus grad P plus mu u by L square into del star square u star. Or if I bring this rho u square by L to the right hand side, I see that it's del u star by del T plus u star dot grad u star is equal to minus grad star P star plus mu u by L square divided by rho u square by L. So, mu u by L square into L divided by rho u square times del star square u star. So, 1L will go, 1U will go, and you get this quantity as mu divided by L rho u, right? Purple shirt again, ask. Tell now what is that? Instead of asking your neighbor, you could ask. That's what I said. That's okay? So, what non-dimensional number did we end up with? Reynolds number, okay. In other words, it's dou u star by dou T star plus u star dot grad u star equal to minus grad P star plus 1 by Reynolds number times del star square u star. That's the non-dimensional form of the momentum conservation equation. Okay, you can see that there are now non-dimensional variables which are u star, t star and p star, and there is only one parameter, and that parameter is nothing but the Reynolds number. Okay, depending upon what is the Reynolds number, you can have equation, the form of the equation will remain the same, but the answer will come out to be a function of Reynolds number. Okay, that's where Reynolds number actually plays a very important role. You know that, for example, Reynolds number is very small, you get laminar flow. When it is very large, you get turbulent flow and so on. Okay, so you are actually ending up with different solutions based on one non-dimensional parameter. It doesn't matter what is the size of the pipe you are using, what is the fluid that you are using, it only matters what the Reynolds number is. That's what the equation or the non-dimensionalization of the equation that just said. Clear? Should I repeat? I'm just saying that we have, really non-dimensionalized our governing equation. When we non-dimensionalize the continuity equation, okay, it did not give you any non-dimensional parameter. We have non-dimensionalized the momentum conservation equation, and we have ended up with just one non-dimensional parameter, and that parameter is Reynolds number. Remember, when we had our original problem, okay, we had S star as a function of T star comma alpha, right? So, the trajectory of the particle, we said alpha determines what is the relation between S star and T star, where S star was some non-dimensional distance, T star was some non-dimensional time. And based on the value of alpha alone, we could say where the trajectory is going to be. So, alpha is the only non-dimensional parameter that determines the solution. Similarly, here this is a partial differential equation. The solution is determined only by Re. Okay, when you solve it, for example, it will come out to be a function of Re. Okay, along with time and space. And the value of Re is that something going to be different, right? You can take one pipe, let's say case 1, and another pipe, case 2. In each case, you can select some Reynolds number 1. This is another Reynolds number 2, okay, and you can, let's say, let a fluid go in and out, okay, and let's say you will select different fluids. So if by the way you are selected different fluids, you are going to get 2 different Reynolds numbers. The flow is going to be different, and it will be different simply based on the Reynolds number, nothing else. That's all we are trying to say, and that's all what the equation has said. Okay. Again, any doubts? Yeah. Yes, so in this particular case, I have kept it same, but otherwise you could take a bigger pipe, you could take a smaller pipe. So that's why, see, we are talking about, for example, T star or length. Okay, when you take out the solution in terms of an X star, it doesn't matter what the actual dimension is. Let's say if you are talking about a small pipe, and then you are talking about a large pipe. Let's say in the small pipe, the diameter was R1. In the large pipe, let's say the radius is R2. In the small thing, we would have the non-dimensional R star would be R divided by R1. Here, R star would be R divided by R2. So this R star would vary between 0 and 1. Here, the R star would vary between again 0 and 1. Okay, so in the scale of that 0 and 1, whatever velocity that you get, okay, will remain same. Here, you mean on the one on the left hand side and the one on the right hand side. So let's say you are looking at a point R star is equal to 0.5. Here also you are looking at a point R star is equal to 0.5. Your equations would give you a U star here. Here it will give you a U star. This U star, the U star on the left hand side and the U star on the right hand side is going to be same. But the absolute magnitudes will be different, because in this case you would have non-dimensionalized U star with some characteristic velocity, which you would have defined it as small u divided by some capital U1. In the right hand side, you would have defined your U star as some velocity divided by, sorry, you don't need that, divided by U2. That means this U that you are going to get in the bigger pipe and this U that you are going to get in the smaller pipe, the numbers would be different. Okay, but this U star would be same in both the cases. Yes. No. Oh, okay. Sorry. So I'm talking about here as Reynolds number being different, and therefore Reynolds number is the parameter. If you want to get this Reynolds number in problem 1 should be same as Reynolds number in problem 2. Then only you get this match. And that's the beauty of talking about it. We don't care about what are the actual dimensions or the fluids. Okay. In fact, this is a very important principle that is used when you have to make, models in a lab instead of testing out in a field, which we'll discuss next week. And this is a principle that we would use. Okay. Okay. So what we have done so far, okay. 2 cases. One was the trajectory of the particle. Second is the governing equation. And these 2 cases are when we knew the form of the equation, and therefore we have gone ahead and done the non-dimensionalization. Now in most of the cases, we wouldn't know the equation, because if we knew the equation, we could have solved it in some way. Okay, so we would not know the equation. We would probably know what are the relevant variables and how would we simplify that situation. That's what we are going to look at. Okay, and there are 2 methods for doing it. The first method is what you call the Buckingham Pi Theorem. And then there is an Ibsen's method, which we'll see if we have time today. So the situation that we are going to consider is the situation that we actually started talking about when we started non-dimensional analysis, which is flow past a body. Okay, we have some object, you know, of some characteristic size L, and then there is a fluid that's going to go past it. Okay, and one of the questions that we posed was, what is the force that this object would exert on the fluid? Because we know that this, we are keeping the object stationary, that means the fluid is going to slow down. So that means the object is exerting some force on the fluid flow. Okay, and you want to know what is that force. We even hypothesized a form for that, right? So let's say that if the fluid is coming with a velocity u and the fluid has a density rho and viscosity mu, then we said the force will be a function of the, the velocity with which the fluid is coming, the size of the object, the density of the fluid, the viscosity of the fluid, and so on, right? And this is the example that we chose, where we said we have force 1, 2, 3, 4, 5 different variables, and if we want to do an experiment, we will do huge number of combinations, and therefore then it becomes, a large data analysis problem rather than making sense out of it. Okay, so we said it can be further simplified. Okay, in this case now we do not know what is the force that's going to be exerted, but we can still calculate some form of the force. Okay, and Buckingham theorem tells you how to do that. We'll do the proof on Monday. We'll just follow the procedure first and see what the procedure is, and then we will prove that what we have done is right. Okay. So, right. So, the steps involved, step 1 is list the variables involved in the problem. Now, this is a very crucial step, because you're starting from nowhere. Okay, you don't know what are the variables involved, but you could do, let's say, some preliminary experiments, vary something and see that things are different, which will give you some idea about what might be the variables involved. Okay, and when you start working on a problem, let's say you are trying to analyze a reactor, you will have some idea, okay, maybe the size is important, some of the fluid properties are important, the, things like that. So it's the selecting the variables. Okay, it's actually a skill and there is no real way of doing it. So in this particular problem, I said, okay, we know that the fluid, the speed with which the fluid is coming, it can be an important parameter. The size of the object, it does look like, it can be an important parameter. I did not say, for example, the thermal conductivity of the fluid is important, because one wouldn't expect that. I did not say the surface tension is important, because there is no really surface involved. Okay, so so you should not select too many parameters, because then it's not going to give you any simplification. The thing that you should really look for is what could be the relevant parameters. You could keep adding it to this later and see whether things are different or not. So in this particular problem, we have taken now 5 different variables, right? Force, length, velocity, density, and viscosity of the fluid. These are the 5 things that we have. And our objective is to now derive an equation which will be a non-dimensional equation. So, first thing is done, list the variables involved in the problem. Step 2, write down the dimensions of each variable. So, we have force, we have velocity, we have a length, we have a density, we have a viscosity. Units of force in terms of MLT, mass, length and time. right? Mass into acceleration, velocity, length per time, length is just length, density is mass per unit volume, viscosity is stress by strain. So, stress is Newton per meter square. So, force mLt to the power minus 2 meter square L to the power minus 2 divided by strain rate T to the power minus 1. So, that is the dimensions of the viscosity, right? Okay, so this is the next step. So what we need to do now is we have got 5 variables, we have got the dimensions of them. Now we have to select a number from it, okay, which I am going to call j, and I will select j to be the number of dimensions involved. So in the problem we have length, mass and time, 3 dimensions involved. So I will select j to be 3 to start with. Okay, I will select j equal to 3 and then I will select j equal to 3, and that means I have to select now 3 variables from 5 variables that I know. Okay, so the 3 variables that I will select, I could select any 3 variable. So right now I am going to select length, velocity and density as the 3 variables. Now when I select them, what I need to ensure is that they do not form a non-dimensional number by themselves. So let's say if I select L, U, rho, so L has the dimension of length, U has the dimensions of LT inverse and rho has the dimensions of M L to the power minus 3. Can you write rho, L and U in any combination that you like so that it can become non-dimensional? No, right? That's because one thing is that rho has an M in it. There are no other quantities which has got mass in it. So whatever way you write, that M is not going to go away. Similarly, U has a T in it. Okay, so that T is anyway not going to go away. So you can ensure, so now you are assured that L, U and rho just cannot form a non-dimensional number. Okay, so these are the variables which we call are the repeating variables, which will be part of each non-dimensional group that you are going to find. Okay, you will find actually some non-dimensional groups. Each of them will have L, U and rho as part of the non-dimensional group along with something else, and that along with something else is something we need to find. For example, if you are not able to find, say we have selected 3 and we are not able to find variables which are not forming non-dimensional group, then we should reduce it. We should reduce the value of j by 1, which basically says instead of looking for 3 variables, select 2 variables as the repeating variables and proceed. Is that clear? Okay. So we have got LU rho. Yeah, now it's easy. Step 4, add the additional variables to form pi groups. So we have LU and rho. The variables that we haven't considered yet are force and viscosity. So we can form 2 pi groups, one with F and one with mu. So our first pi group, which I'll call pi 1, is going to be just F times L to the power A, U to the power B, rho to the power C. So L, U and rho are my repeating variables. I raise each of them with a certain power. I multiply it with some force, okay, and that's what I am going to call my first non-dimensional group to be. I do not know what ABC are, but it's likely that there might be an ABC which might exist, which can give you a non-dimensional group. Okay. Ask? No? Okay, I'll take a pause and I'll take questions. Okay, let me repeat what we have done so far. Maybe then that will help. What is our problem right now? We have a object, we have a fluid that is flowing past it. Okay, and we want to know what is the force that this object is going to exert on the fluid. Okay, you are clear that the fluid is going to slow down, right? Because you have kept an object there, so the fluid is going to go slow down. Fluid was actually coming with a velocity u, okay, and it's going to go down to some other velocity which we do not know, but our interest right now is to find out what is this force. Okay, now this is a very important problem, as you will see many applications of this. So that's the objective that we have. Okay, now we do not know anything. One possibility was that we solved the governing equations, so okay, which were complicated equations, and you knew, I mean, you have actually seen that only in certain situations you can solve it. Okay, this particular problem is a very difficult problem. Okay, you don't know exactly at the moment how to solve it, so you are actually trying to do an alternate approach. That alternate approach is what we are trying to learn right now. Okay, so it involves certain number of steps, and we are just going to follow those steps and see what we are going to end up with. Okay, and that result is what is one calls as Buckingham Pi Theorem. Okay, basically it's a theorem that tells you that how many non-dimensional variables you can identify, and there exists a relation between those non-dimensional variables. So I'm telling you that we will do the proof on Monday. We'll just follow so that we are familiar with the the idea of dimension, so that the proof becomes simpler. So the problem now is to calculate the force. We are it will depend on the shape of the body. So how would you include the shape? What is that? Angle does not have dimension, so I don't care. What else would you include? Okay, so you are right. So for example, if it was a rectangle, then we could have chosen 2 different lengths, right? Or if it was a star, I could have chosen multiple lengths. Okay, so right now I am assuming that there is only one particular length that is relevant for my problem. If you wanted to actually do a rectangle, you could define an A, you could define a B, and you can say it's a function of A and B. So if you like, you can assume right now that it's a sphere of diameter L. How do you know B does not have any effect? See, fluid is going to go like that, right? So the regions of B, it's coming in contact a lot. There you are applying the no-slip boundary condition. The fluid is indeed going to go down, right? Whether it's a smaller one or whether it's a longer one, the fluid will slow down up to different extent. Which surface area? Of the object. So you could, so that you are saying that A into B is your non-dimensional parameter. Sorry, it's a dimensional parameter that you are worried about. I don't know at the moment whether A into B is the right parameter or is it something else. So I'm going to keep my A and B separate. I'm not even caring about right now in the problem. I'm just saying L is the only parameter that I'll worry. Okay, so I'll continue. So this is, so we have written down now a expression, not really an expression, just a functional form where we have said that f is dependent on the other 4 variables in the problem, which we have identified as velocity, length, density and viscosity. Okay, so we have got 5 variables and we know the dimensions of each of them. We have identified the dimensions of each of them. That was step number 2, simply writing down what is it in terms of mass, length and time. That's a simple thing to do, right? Now I'm saying that we have to, the next step really is to, tell how many non-dimensional groups are there. Okay, that's why we are coming up with this variable j. Okay, so let me state the, no, it's okay. So we are now out of this 5, we have to select. So it's like selecting the scaling parameters. When we did the trajectory, right, we selected 2 scaling parameters. Okay, so here we are actually going to select 3 of them. Okay, and these 3 are L, U and rho at the moment. We have taken L, U, rho, and I'm saying that we can form 2 groups which we will call pi groups containing L, U and rho, pi 1 and pi 2. So L to the power A, U to the power B, rho to the power C. So these are the 2 pi groups that I am writing down. In the first pi group, I have put all the 3 variables. In the second pi group also, I have put all the 3 variables. Okay, LU, rho, LU and rho. In the first one, I have added my force. In the second one, I have added viscosity. So now you can see that I have covered all the 5 variables. I'm not saying, so this let's call it A1, B1, C1 and let's call this A2, B2 and C2. I do not know whether what are the values of A1, B1 and C1. Okay, but all of them have got some dimensions. So I may be able to find out some A1, B1, C1 such that it forms a non-dimensional number. So let's try to find out A1, B1, C1. Okay, so how would we do that? If we talk about pi 1, okay, that is f times L times U times rho. So f has the dimensions, let me write again, f times L to the power A, U to the power B, rho to the power C is, f has the dimension of mass, length, t to the power minus 2 into length has the power of length, U is L, t to the power minus 2 to the power B, rho is M, L to the power minus 3, and if I want that to be a non-dimensional number, that is nothing but it has to be M to the power 0, L to the power 0, t to the power 0. That means I can now write down, if I talk about, let's say, mass, if I compare the comparing each dimensions say length, for example, m, if I do this, there is an m to the power of 1, there is an m to the power of c, and that will give me a 0. That means 1 plus c should be 0, and therefore c should be equal to minus 1. Correct? What will time give? Minus 2 minus 2b should be equal to 0. So that means b is equal to minus 1. Which one did I do? This is 1, no? So that means it has to be minus 2, and then this is minus b, and therefore b has to be equal to minus 2. Find out a by comparing length. Tell what is a. Oops, it's time now. What is a that you got? Minus 2. So let's just write down the parameter and stop. So that means we have calculated pi 1 as f L to the power, did we write L? L to the power minus 2 u to the power minus 2 rho to the power minus 1. Okay. So that's basically f divided by rho u square L square. That's one of the non-dimensional parameters that we have gotten. We'll do the rest tomorrow.